We're going to chapter 8 deals with the moon and Mercury. And it might seem strange at first that you have, and these are called scorched and battered worlds. Because at first glance, the moon and Mercury appear to be very, very similar. They'll have a lot of the same surface features, but there are some particular differences that we'll talk about. And we'll look at why these things are actually grouped together. They're not terribly different in size. So let's look at the moon and Mercury. So in order to actually find the distance to the moon, well, we've been to the moon, but what you would really need to do, if you really wanted to, if you were planning on sending a rocket to the moon, you'd really want to know exactly how far away it was at any given point in time. And you could use parallax to do this. You could use radar ranging. You could use laser ranging, which is the most accurate way to do this. And it's actually been possible now to find the distance to the moon from some particular point in space. Since we've been to the moon already and we've actually put mirrors or reflectors onto the surface of the moon, you can aim from the Earth a laser beam to one of these mirrors, and it's possible to measure very, very accurately, because we can tell within a very, very small period of time exactly how long it takes for a laser to leave the Earth, to go to the moon, and then return. And it's approximately 2.56 seconds. But from that, it's been possible to actually calculate the distance from the Earth to that particular point to within a few centimeters of accuracy. So if you can imagine that over a distance of something like 384,000 kilometers, the approximate distance from the Earth to the moon, to actually be able to hit that within a few centimeters is really, truly remarkable. The moon's angular diameter is 0.5 degrees, so it's a half a degree. So that's fairly large if you think about it. That's, there are 360 degrees for the entire sky, not just the part that we see, but the part underneath us as well. If we went all the way around, and a half a degree of that is actually taken up by the moon. The moon is about approximately 1,938 kilometers in radius. Mercury itself has a much, much smaller angular diameter. Its angular diameter is only about 13 seconds. Remember that there are 1 degree is divided into 60 minutes, and each one of those minutes is divided into a second. So this is 13 over 360, whatever that fraction comes out to be, of a degree. So it's a much, much smaller angle, as you would expect, because as you go to a more distant object, if the moon is here and we're here and we're looking at it, we're going to get a fairly, but if Mercury's all the way out here, then we practically got a straight line from one side to the other. And Mercury is much more than what I've actually shown here. The moon's average density is 3,300 kilograms per cubic meter. That comes out to about 3.3 grams per cubic centimeter. And for the Earth, that average value is around 5,500, or 5.5 grams per cubic centimeter. So the moon, this is another thing that's kind of interesting, because there are some theories that in terms of how the moon was formed, that the moon could have been formed from the Earth, but certainly not just a chunk of the Earth splitting out, because the densities are quite a bit different. This density is only about 60% of that density, so that doesn't seem to make a lot of sense. But we'll talk about that in a little bit. So what we would say about the moon is that there must be fewer of the heavy elements that we have on Earth. So we wouldn't expect to see a lot of the heavier elements. The moon will be composed more of the lighter elements, and from the moon rocks that we brought back, we know this to be the case. A lot of silicates, which are kind of light materials. A lot of things. Maybe things like aluminum, and maybe not so much iron, for instance. A lot less than we would have on the Earth. So the kinds of things that make the Earth heavy are pretty much missing on the moon. The gravity of the moon is about 1/6 of Earth's gravity, so say about 0.16 of Earth for the moon, and for Mercury it's 0.40. And other things that we should know about the difference. Oh, the other thing is I didn't mention Mercury's density. So Mercury, about 5,400 kilograms per cubic meter. Well, very close to the density of the Earth. So we might think that, whatever kind of material was used to form the Earth, maybe the same material was used to form Mercury. That being the case, we'd expect Venus and Mars to also have densities similar to this, and in fact they do. So we'll talk about that later, but nevertheless, so we've got the idea of the density of the moon being considerably different than the density of Mercury. But nevertheless, the features on the moon look a lot like the features on Mercury. Looking at the moon from the Earth, we see some areas that are dark and some areas that are light. And the idea of the man in the moon, what appears to maybe be a face on the moon, was because you had light areas and dark areas, and people would look up at that and think that maybe they saw a face in there. But the dark areas are known as Maria. Singular is mare, and this is the Latin word for seas. And we also have light areas, which are generally referred to as the highlands. So the lighter areas have much greater elevation. The so-called seas, they're not really seas, and there was never any water there, or if there was, it certainly leaked out billions of years ago. And if we actually look at the chemical composition of rocks that would be taken from highland areas and those that were taken from the Maria, what we find is that they're considerably different, that they're lighter. The Maria have much more iron in them than the highlands do. So the dark color could very well be from the fact that in the Maria, that those particular areas, these dark areas, might have a lot more iron. And if you look at that from the Earth, the iron, which is maybe not in the form of iron oxide, but it could be in the form of iron oxide, that appears to be much darker in color than the other material, which is much richer in things like aluminum, which is a lighter element. So in the highlands, densities are on the order of rock densities are on the order of 2,900 kilograms per cubic meter, and in the Maria, it's closer to the average value of 3,300 kilograms per cubic meter. That would also indicate that since this is less and that's just around the average value, there must be some other area that's somewhat more dense than that. So there may be even more iron-rich material, perhaps a small core of iron, we don't really know, at the center of the moon. But that is a possibility. We didn't mention one of the features that you have on both Mercury and the moon, which are craters from impacts of either asteroids or meteoroids. You see that on the surface of both planets. Now, if you're looking, and the craters on the moon are generally about 50 to maybe 500 kilometers in size. Well, there's also very small craters as well. But the more visible craters, the ones that we've actually named, tend to be in that range. There's also microscopic craters. So, for instance, they've brought back little spheres of these small, like glass buttons of silica, which were probably formed when something impacted, could have been millions of years ago, or even way before that. Something impacted on the surface of the moon, heated this up. You've got these little glass craters. Some of these things actually have from micro meteoroids, from extraordinarily small meteoroids. Some of these things were actually impacted, and you can actually see micrographs of these. You can actually see craters on the surface of these, and they look very much like the craters that are actually on the surface of the moon. So you get that same kind of cratering from very, very small micrometeoroids. The rotation of the moon. The moon rotates synchronously with the Earth. That means that as the moon rotates, as the Earth rotates about its axis, the moon is rotating in such a way, it's also rotating about its axis as it's moving around the Earth, but it does it in such a way that as it's moving around the Earth, it's rotating in such a way that it's always showing us the same face. So the side of the moon that we see is always the same face. And until man actually landed on the moon, or until, well, actually before that, when it was possible for ships to actually orbit the moon, no one had ever observed the dark side of the moon, but we now have information regarding the dark side of the moon as well. Mercury has also been photographed many, many times. Mariner 10 in 1974, at a distance of 10,000 kilometers, took about 10,000 pictures of Mercury's surface. And the Messenger probe in 2008 gave us better images. Now, what you do see on Mercury that you don't see on the moon are that a lot of these areas, especially where there are craters, there's a halo of material around the crater. So it's like a dark halo, and nobody knows yet what that is. But there's some dark material forming around there. And Mercury's orbit is said to have a 3-to-2 resonance with the Sun. So as Mercury goes around the Sun, every day, every Mercury day is 2 Mercury years in length. So it takes 2 complete orbits before it presents the same face to the Sun. Neither the Mercury nor the Moon actually have any atmosphere. And the reason for this actually has to do with escape velocity. We mentioned this a little bit. I don't remember whether it was last week or in the first week, but I did mention, I did talk about escape velocity. We had a formula that we could use to find out what the velocity of an orbiting object happens to be. And I did mention that at about 1.414, the square root of 2 times that velocity, that object would be going fast enough that it would actually have what we call an escape velocity, and it would actually leave, it would no longer orbit that planet or that other object. So it turns out that there is a formula that we can use to find the escape speed in kilometers per second. And if we want to do that for any planet, we can just say that the escape speed is going to be equal to 11.2 times the square root of the mass of that particular body in Earth masses. So that means that, for instance, for Earth, the mass would just be 1. For something that's twice as massive, that weighs that would have twice the mass of the Earth, its mass would be 2, etc. Divided by the radius of the body in Earth radii. So clearly, if we're talking about the Earth, this is 1 over 1, and it's just going to be 11.2 is the number that we're talking about. So 11.2 kilometers per second is actually the speed that something needs to have on the Earth in order to be able to pull away from Earth's gravitational field. Turns out that that speed is about 18,000 miles per hour. That's the speed of a satellite in orbit, and about 1.4 times that comes out to 25,000 miles per hour, and that's considered to be escape velocity. I think that's about 7 miles per second, if memory serves me correctly. So if you're going 7 miles per second or faster than that, you're not going to be able to remain in a stable orbit, and you'll actually be expelled from the Earth's orbit. And you could use, as I say, you could use this same formula then to calculate for any other planet, just comparing its mass and its radius, and we could figure out what its escape speed would be. So there is another formula that we need, which is the formula that will tell us the average molecular speed of any molecule, whether it's on the Earth or somewhere else. And this is going to be dependent on not only on gravitational considerations, but it's also going to depend on things like temperature, etc. So what we've got is that the average molecular speed is going to be equal to 0.157 times the square root of temperature of these are gases, so it's the gas temperature in Kelvin divided by the molecular mass, and that's in your book says it's in hydrogen atom units, but the mass of it's basically what we're just doing is we're looking at the atomic mass here. So hydrogen has an atomic mass of 1. Oxygen has an atomic mass of 16. Nitrogen is 14. So we can actually put in, plug in these values and get information from that. If we're looking at molecules, it's actually twice that. So nitrogen would be not 14, it would be 28, because nitrogen is N2 and oxygen is O2. So if we wanted to do that for nitrogen, we'd plug in the value 28 and we plug in the value 32 for oxygen. And we have to use the Kelvin scale of temperature as opposed to the Celsius, because in order for this to work, we can't have negative numbers. And we need a scale that goes from 0 to some positive value, something that has no negative values in it at all. So Celsius would not work in this kind of a situation. So all of our scales have to begin at 0 and then go up from that point. We use Kelvin. Anyway, so if we were to actually do this, for instance, for let's say for nitrogen, we would find that for nitrogen, we would get a value of 0.157 times the square root of, let's say, at an average Earth temperature, 23 degrees Celsius. This would be a relatively warm day. It'd probably be a day in the mid-70s or something like that. But at that particular temperature, that's 300 Kelvin, we'd have the square root of 300 divided by 28 for nitrogen. That comes out to a value of 0.51. And this value is in kilometers per second. So that's 0.51 kilometers per second. And if we did the same thing for oxygen, we get a value of, so that's 300, the square root of 300 divided by 32. We get a slightly smaller value of 0.48 kilometers per second. Well, here's the deal. If at approximately 6 times the average molecular speed, if you're greater than that speed, that's the escape speed. If the gases will leak away gradually. Below that speed, if gases are actually below that speed, they'll either leak away very, very slowly, or they'll remain around for a very long period of time. So if you look, we already saw what the escape speed was on the Earth. It would be 11.2. If you look at the values here, even if we multiply these by 6, we're only at a value of about 3 kilometers per second. So we're well below the escape speed. Now that doesn't mean, however, that nothing ever escapes our gravitational field, that molecules don't escape their gravitational field, because there is a small finite probability that some molecules will have enough kinetic energy that they will actually reach, you're only talking about maybe fourfold increase in energy. So some molecules are going to be hotter and some will be cooler. If we actually looked at the distribution of the molecules, they'd probably be normally distributed. This would be the average value. There'd be a small percentage of them that would be moving very, very slowly, and there'd be perhaps an equal small percentage of them that were moving rather rapidly. And some of those things are going to leave. But it turns out that if your gravity is much lower than that, and I don't have the figures for the moon, but you can see certainly the moon in Earth masses is going to be a lot smaller. Its radius will be smaller as well, but nevertheless the escape speed from the moon is going to be a lot less than this. The escape speed for Mercury will be such that the actual speed of if there were oxygen or nitrogen at some point in time on the formation of Mercury, even if those gases were present, they would have boiled off. Also, Mercury being so much hotter, that temperature is also going to play into this. So since that's in the numerator, we know that the hotter temperature of the surface of the planet is going to cause that to, and again, the moon as well, even though there's a big discrepancy in temperature, the face of the moon, the part that's facing the sun, gets to be quite hot. So again, we've got that increase in temperature. So it turns out that for the moon or for Mercury, you would not expect there to be any atmosphere whatsoever.